Introduction to Network Connectivity Comparison. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In today's presentation, we'll be exploring how the three major cloud providers handle global network connectivity. Specifically, we're going to compare Google Cloud Platform's Network Connectivity Center with Amazon AWS, Transit Gateway, and Microsoft Azure's Virtual WAN. These are the foundational services that enable enterprises to build hub-and-spoke network topologies at scale. Understanding these services is critical for cloud architects and network engineers who need to design multi-region, hybrid cloud architectures. Each provider approaches the problem differently, with unique features, pricing models, and architectural patterns. By the end of this presentation, you'll understand the key capabilities of each service, their similarities, their differences, and most importantly, when to choose one over the other. We'll start by examining the problem these services solve. Then we'll dive deep into each provider's solution, comparing their architectures, features, limitations, and use cases. This comparison will help you make informed decisions when designing your cloud network infrastructure. Introduction to GCP Network Connectivity Center. Google Cloud Platform's Network Connectivity Center, commonly abbreviated as NCC, is Google's solution for implementing hub-and-spoke network topologies. NCC is a fully managed service that acts as a central hub for connecting your entire network infrastructure, whether it's in Google Cloud, on-premises, or in other clouds. What makes Network Connectivity Center particularly powerful is its tight integration with Google's global network backbone. When you use Network Connectivity Center, your traffic benefits from Google's private fiber network, which spans the globe and provides low-latency, high-bandwidth connectivity. This is the same network that powers Google Search, YouTube, and Gmail, so you're leveraging one of the world's most robust network infrastructures. NCC operates at a global scale by default. You don't create regional hubs. Instead, you create a single NCC hub that automatically spans all Google Cloud regions. This means a spoke in Asia can communicate with a spoke in Europe through the same hub, without you having to set up inter-region connections manually. The service handles all the complex routing automatically. Looking at the architecture diagram, we see the Network Connectivity Center hub positioned at the center. This hub is a logical construct that exists globally across Google's network. Connected to this hub through spoke attachments, we have several types of connections. First, we see VPC spokes, which are Google Cloud virtual private cloud networks that need to communicate with each other or with external resources. These VPC spokes connect to the NCC hub through spoke attachments. Next, we have hybrid connectivity spokes, which represent connections from on-premises data centers to the NCC hub. These connections typically use cloud VPN tunnels for encrypted connectivity over the Internet, or cloud interconnect links for dedicated, private connections. The diagram shows these as separate paths because they represent different connectivity options with different characteristics. We also see router appliance spokes, which are particularly interesting. These represent third-party network virtual appliances, such as software-defined WAN solutions or security appliances from vendors like Cisco, Palo Alto, or Fortinet. By connecting these appliances as spokes, you can integrate advanced routing features or security functions into your NCC topology. All of these spokes connect to the central hub, which handles routing between them. The arrows indicate bidirectional traffic flow, meaning any spoke can communicate with any other spoke through the hub. NCC automatically manages the routing tables and ensures that traffic follows the most efficient path through Google's global network. The key architectural principle here is that Network Connectivity Center is not a physical device or a regional service. It's a global, software-defined networking layer that orchestrates connectivity across Google Cloud and beyond. This makes it incredibly flexible and scalable compared to traditional hardware-based hub and spoke solutions. Introduction to AWS Transit Gateway. Amazon Web Services offers Transit Gateway as their solution for hub and spoke network architectures. Transit Gateway, often abbreviated as TGW, is a highly scalable network transit hub that connects virtual private clouds and on-premises networks through a central gateway. What distinguishes Transit Gateway is its regional architecture combined with inter-region peering capabilities. Unlike network connectivity centers' global by default approach, each transit gateway is deployed in a specific AWS region and connects VPCs within that region. However, you can peer multiple transit gateways across regions to create a global network topology. This regional approach gives you fine-grained control over network boundaries and data residency. Transit Gateway is one of AWS's most popular networking services because it dramatically simplifies network architecture. Before Transit Gateway, connecting multiple VPCs required either VPC peering connections, which create a complex mesh, or routing traffic through a central VPC with software routers, which creates a bottleneck. Transit Gateway eliminates these problems by providing a managed, scalable hub. Looking at our architecture diagram, we see the Transit Gateway positioned as the central hub. This is a managed AWS service that operates within a specific region. Connected to the Transit Gateway are several types of attachments, which are how resources connect to the gateway. First, we have VPC attachments. These represent virtual private clouds within the same region as the Transit Gateway. Each VPC attachment connects one or more subnets from a VPC to the Transit Gateway. Traffic from the VPC flows through these attachments to read other spokes. Next, we see VPN attachments, which represent site-to-site VPN connections. These are typically used to connect on-premises data centers or remote offices to the Transit Gateway. The VPN provides encrypted connectivity over the Internet, making it suitable for scenarios where dedicated connections aren't available or cost-effective. The diagram also shows Direct Connect gateway attachments. AWS Direct Connect is a dedicated network connection from your on-premises data center to AWS. By connecting Direct Connect to Transit Gateway through a Direct Connect gateway, you get private, high-bandwidth, low-latency connectivity between your data center and all VPCs attached to the Transit Gateway. Additionally, we have Transit Gateway peering attachments. These represent connections between transit gateways in different regions or even different AWS accounts. Peering allows you to extend your hub and spoke topology across regions while maintaining regional boundaries. Traffic between peered transit gateways flows over AWS's private backbone network. All of these attachments connect to the central Transit Gateway, which handles routing between them. The bidirectional arrows indicate that traffic can flow in both directions through the gateway. Transit Gateway supports up to 5,000 attachments per gateway, making it suitable for very large enterprise environments. The regional nature of Transit Gateway means you have explicit control over which resources can communicate across regions. This is particularly important for compliance and data residency requirements where you need to ensure certain data doesn't leave specific geographic boundaries. Introduction to Azure Virtual WAN. Microsoft Azure's approach to global network connectivity is Azure Virtual WAN, which Microsoft often refers to as vWAN. Virtual WAN is a networking service that brings together many networking, security, and routing functionalities into a single unified interface. It's Microsoft's most comprehensive networking solution, designed to simplify large-scale branch connectivity and global transit architectures. Virtual WAN is distinguished by its integration with software-defined WAN solutions and its strong focus on branch office connectivity. While all three providers support hybrid connectivity, Azure has made Virtual WAN particularly appealing for organizations with many branch offices that need to connect to Azure. The service has built-in partnerships with major SD-WAN vendors, making it easier to integrate existing WAN infrastructure. Virtual WAN operates on a hub and spoke model but with some unique terminology. Azure uses the term virtual hub rather than just hub, and these virtual hubs are regional constructs. However, Azure provides a global transit network architecture that connects multiple virtual hubs together, similar to how AWS peers transit gateways. Let's examine the architecture diagram. At the center, we have a virtual WAN resource, which is the top-level container that represents your global network. Think of this as the management plane for your entire virtual WAN deployment. Under this virtual WAN resource, we see multiple virtual hubs, each positioned in a specific Azure region. Each virtual hub acts as a regional hub, connecting resources within its region and providing transit routing. The first virtual hub in the diagram connects to several types of resources. We see VNet connections, which are virtual network attachments. These represent Azure virtual networks that are associated with the hub. Traffic from these VNets can flow through the hub to read other destinations. We also observe site-to-site VPN connections emanating from the virtual hub. These connect branch offices or on-premises data centers to the hub using encrypted VPN tunnels over the Internet. Azure Virtual WAN supports highly scalable VPN connectivity, with a single virtual hub capable of handling thousands of VPN connections. The diagram shows Express Route connections, which are Azure's dedicated private network connections. Express Route provides high bandwidth, low latency connectivity from on-premises locations directly to Azure, similar to AWS Direct Connect or Google Cloud Interconnect. Express Route connections terminate at the virtual hub. Additionally, we see point-to-site VPN connections, which are designed for individual remote users rather than entire sites. These allow mobile workers or remote employees to connect securely to the virtual hub and access resources in connected VNets. Point-to-site uses client VPN software on the user's device. Finally, the diagram illustrates connections between virtual hubs themselves. These inter-hub connections create a global transit network. Traffic can flow from a spoke connected to one virtual hub to a spoke connected to a different virtual hub, with the hubs handling the transit routing automatically. These connections use Azure's global backbone network. The key architectural principle of virtual WAN is that it combines multiple networking functions into a unified service. The virtual hub doesn't just route traffic. It can also provide firewall services through Azure Firewall, application delivery through Azure Application Gateway, and SD-WAN integration through partner network virtual appliances. This integration of services makes virtual WAN a comprehensive networking platform rather than just a routing hub. Feature Comparison Matrix. Now that we've explored each service individually, let's compare them side by side across critical dimensions. This comparison will help you understand which service best fits your specific requirements. Looking at our comparison table, the first row addresses the scope of deployment. Google Cloud's Network Connectivity Center operates globally by default. When you create an NCC hub, it exists across all Google Cloud regions automatically. AWS Transit Gateway takes a regional approach, where each transit gateway is deployed in a specific region, but you can create a global network by peering transit gateways across regions. Azure Virtual WAN uses a hybrid model with regional virtual hubs that are connected through a global virtual WAN resource. For connectivity types, all three services support VPN and dedicated connections. GCP supports Cloud VPN and Cloud Interconnect. AWS supports site-to-site VPN and Direct Connect. Azure supports site-to-site VPN, point-to-site VPN for remote users, and Express Route for dedicated connections. Azure is the only one that natively supports point-to-site VPN at the hub level, making it more convenient for remote user connectivity. Regarding routing capabilities, GCP NCC uses Cloud Router with BGP for dynamic routing and supports policy-based routing. AWS Transit Gateway provides multiple route tables per gateway, automatic route propagation from VPN and Direct Connect, and supports both static and dynamic routing. Azure Virtual WAN offers custom route tables, routing intent for simplified policy configuration, and integration with Route Server for advanced BGP scenarios. When we examine third-party appliance support, GCP Network Connectivity Center has excellent support through router appliance spokes, allowing you to integrate network virtual NBAs as first-class spokes in the topology. AWS Transit Gateway supports appliances through appliance mode, which ensures proper symmetric routing, and you can deploy appliances in VPCs attached to the gateway. Azure Virtual WAN has the strongest ecosystem integration with official partnerships with major SD-WAN vendors and support for deploying network virtual appliances directly in virtual hubs. For security integration, GCP relies on separate security services like Cloud Armor and third-party appliances, with security implemented at the spoke level rather than in the hub. AWS Transit Gateway also uses separate security services, typically deploying inspection VPCs with security appliances, but supports centralized inspection architectures. Azure Virtual WAN stands out by offering integrated Azure Firewall directly in the virtual hub, creating secured virtual hubs where all transit traffic can be inspected without deploying separate appliances. Multicast support varies significantly. GCP Network Connectivity Center does not currently support multicast. AWS Transit Gateway supports multicast within a region through multicast domains. Azure Virtual WAN does not natively support multicast, though you can implement it through network virtual appliances if needed. Looking at scale limits, GCP NAT Connectivity Controller theoretically has unlimited scalability as it leverages Google's global network, though practical limits depend on cloud router capabilities. AWS Transit Gateway supports up to 5,000 attachments per gateway with up to 50 gigabits per second of VPN throughput. Azure Virtual WAN supports thousands of site connections per hub with up to 20 gigabits per second of aggregate VPN throughput per hub. The management experience differs as well. GCP Network Connectivity Center is managed through the Google Cloud Console, G-Cloud CLI, and APIs with a relatively straightforward configuration model. AWS Transit Gateway uses the AWS Console, CLI, CloudFormation, and Terraform with a more complex configuration due to the route table architecture. Azure Virtual WAN provides management through the Azure Portal, Azure CLI, PowerShell, and ARM templates, with a focus on simplified configuration for common scenarios. Pricing Comparison Overview. Understanding the cost structure of these services is crucial for making informed decisions. While all three providers charge for these networking services, their pricing models differ significantly. Google Cloud's Network Connectivity Center has a relatively simple pricing model. You pay per spoke attachment per hour. The cost varies depending on the type of spoke. VPC spokes are generally less expensive than hybrid connectivity spokes. There are also data transfer charges for traffic that flows through the NCC hub, but traffic within the same region is typically less expensive than inter-region traffic. One advantage of NCC's pricing is that there's no separate charge for the hub itself, only for the attachments and data transfer. AWS Transit Gateway uses a multi-component pricing model. First, there's an hourly charge for the transit gateway itself, regardless of how many attachments you have. This is essentially a base fee for having the gateway deployed. Second, you pay per attachment per hour for each VPC, VPN, or Direct Connect gateway attachment. Third, there are data processing charges for traffic that passes through the transit gateway. These processing charges apply to all traffic except traffic between VPCs in the same availability zone. Additionally, you pay for inter-region peering, with separate charges for the peering attachment and for data transfer between regions. Azure Virtual WAN has perhaps the most complex pricing structure. There are charges for the virtual hub deployment itself, which is a fixed hourly rate per hub. Then there are connection charges based on the number of connection units, where a connection unit represents a certain amount of throughput capacity. Site-to-site VPN connections are charged per connection unit, which is calculated based on aggregate throughput. Express route connections have their own pricing based on the express route circuit. Additionally, you pay for data processing, which is the amount of data that flows through the hub. If you enable secured virtual hub with Azure Firewall, there are separate charges for the firewall deployment and for the data processed by the firewall. Comparing the pricing structures, GCP tends to be more straightforward, but can become expensive with many attachments. AWS has more granular pricing, which gives you better visibility into costs, but requires careful planning to optimize. Azure's pricing is the most complex, but offers good value for scenarios with high site-to-site connectivity due to the connection unit model. An important consideration for all three is data egress charges. When data leaves a cloud provider's network to the internet or to another cloud, you typically pay significant egress fees. All three providers charge for data egress, and these charges often exceed the networking service charges themselves. For hybrid architectures, you need to consider the cost of data transfer between your on-premises data center and the cloud. Cost optimization strategies differ by provider. For GCP, minimizing spoke count and keeping traffic within regions reduces costs. For AWS, using VPC attachments efficiently and avoiding unnecessary transit gateway hops can help. For Azure, right-sizing connection units and using secured virtual hubs selectively can optimize costs. In all cases, understanding your traffic patterns and architectural requirements is essential for cost-effective design. Use case Global Enterprise Network. Let's explore a common real-world scenario where an enterprise needs to connect resources across multiple regions and on-premises locations. This use case will help us understand how each service handles global connectivity requirements. Imagine a multinational corporation with headquarters in New York, development teams in London and Singapore, manufacturing facilities in Germany, and customers worldwide. The company uses cloud infrastructure as a service for its applications and needs to maintain connectivity between all these locations while ensuring low latency, high availability, and centralized security. Looking at our architecture diagram, we see how each cloud provider would implement this scenario. The diagram is divided into three sections representing GCP Network Connectivity Center, AWS Transit Gateway, and Azure Virtual WAN. In the GCP section, we have a single global NCC hub at the center. Connected to this hub are VPCs in multiple regions including US East 1 for the New York headquarters, Europe West 2 for the London development team, and Asia Pacific Southeast 1 for the Singapore office. We also see Cloud Interconnect providing dedicated connectivity from the German manufacturing facility. The key characteristic here is that all regions connect to a single global hub, and Google's backbone automatically handles inter-region routing. In the AWS section, the architecture is different. We see three separate transit gateways, one in each region: US East 1 for New York, EU West 2 for London, and Asia Pacific Southeast 1 for Singapore. Each regional transit gateway connects to VPCs in its region. The German manufacturing facility connects via Direct Connect to the EU West 2 transit gateway. Between the transit gateways, we see peering connections that link them together. Traffic between regions must traverse these peering connections. This regional approach provides explicit control over inter-region traffic. In the Azure section, we have a virtual WAN resource as the top-level container. Under this, we see three virtual hubs deployed in East US, UK South, and Southeast Asia regions. Each virtual hub connects to VNets in its respective region. The German manufacturing facility connects via express route to the UK South hub. The virtual hubs are interconnected through Azure's global transit network, allowing any-to-any connectivity while maintaining regional deployment boundaries. The flow of traffic differs between platforms. In GCP, traffic from Singapore to New York flows directly through the global NCC hub over Google's backbone. In AWS, The same traffic would go from the Singapore VPC to the Asia-Pacific Southeast 1 Transit Gateway, then across the peering connection to the US East 1 Transit Gateway, and finally to the New York VPC. In Azure, traffic flows from the Singapore VNet to the Southeast Asia Virtual Hub, then through the Global Transit Network to the East US Virtual Hub, and finally to the New York VNet. Each approach has trade-offs. GCP's single global hub is simplest to configure and provides optimal routing automatically. AWS's regional approach gives you more control over inter-region traffic and makes it easier to implement region-specific policies. Azure's model balances these with regional hubs that are globally connected, providing both control and simplified management. Use case multi-cloud architecture. Multi-cloud architectures are increasingly common as organizations seek to avoid vendor lock-in, leverage best-of-breed services from different providers, or meet specific regional or regulatory requirements. Let's examine how these hub services facilitate multi-cloud connectivity. Consider a media streaming company that uses AWS for its primary content delivery infrastructure, Google Cloud for machine learning and analytics on viewer data, and Azure for Microsoft-specific services like Active Directory integration. The company needs these three cloud environments to communicate for tasks like user authentication, analytics data sharing, and backup replication. The architecture diagram illustrates a multi-cloud topology where all three cloud providers are interconnected. At the center, we see three hub services: GCP Network Connectivity Center, AWS Transit Gateway, and Azure Virtual WAN. These hubs need to connect to each other to enable multi-cloud communication. Starting with the connections from AWS to GCP, we see VPN connections between the AWS Transit Gateway and GCP Network Connectivity Center. Specifically, AWS site-to-site VPN connections are established that connect to GCP as if GCP were an on-premises location. In GCP, these VPN tunnels terminate at Cloud VPN gateways, which then connect as spokes to the NCC hub. This creates an encrypted tunnel over the internet between the two clouds. The VPN connections use Border Gateway Protocol to dynamically exchange routes, so each cloud learns about the other's network prefixes. Similarly, connections from AWS to Azure use site-to-site VPN between the AWS Transit Gateway and Azure Virtual WAN. The Azure side terminates these VPN connections at a virtual hub's VPN gateway. Both clouds exchange routes via BGP, enabling seamless connectivity between AWS VPCs and Azure VNets. For GCP to Azure connectivity, we see VPN tunnels between GCP Cloud VPN and Azure Virtual WAN's VPN gateway. These establish encrypted connectivity with dynamic route exchange. An important consideration in multi-cloud architectures is the potential for higher latency and lower bandwidth compared to single cloud deployments. Traffic between clouds must traverse VPN tunnels over the internet, unless you use dedicated interconnection services. Some colocation facilities and internet exchanges offer direct cross-connects between cloud providers, which can improve performance but add complexity and cost. Another approach to multi-cloud connectivity is using a third-party SD-WAN solution. The diagram shows an alternative path where each cloud connects to an SD-WAN provider's network. The SD-WAN provider has points of presence in or near each cloud provider's data centers, and maintains a private backbone network. By connecting each cloud to the SD-WAN network, you can route inter-cloud traffic over the SD-WAN backbone, potentially achieving better performance than internet-based VPN. Azure Virtual WAN's SD-WAN partnerships make this integration particularly straightforward. Security in multi-cloud architectures requires careful planning. You need to ensure consistent security policies across clouds, which can be challenging given different security models and tools. Many organizations use network virtual NVAs deployed in each cloud that provide consistent firewall and intrusion detection capabilities. These appliances can be integrated into the hub and spoke topology, For example, in GCP you would deploy a security appliance as a router appliance spoke. In AWS you would deploy it in a VPC attached to Transit Gateway with appliance mode enabled. And in Azure you could deploy it in a VNet or use the built-in Azure firewall in a secured virtual hub. Cost optimization is also critical in multi-cloud scenarios. Data transfer charges between clouds can be substantial. All three providers charge for data egress, meaning data leaving their network. If you're transferring large amounts of data between clouds regularly, these costs can exceed the compute and storage costs. Strategies to minimize costs include keeping data processing in the same cloud where the data resides, using efficient data formats and compression, and carefully planning which workloads need real-time cross-cloud connectivity versus batch transfers. Implementation best practices. Security and compliance. Security and compliance are paramount when implementing global network architectures. Let's examine best practices for securing your hub and spoke topology. The first security principle is defense in depth. Don't rely on a single security control. Instead, implement multiple layers of security. Our architecture diagram illustrates this concept with multiple security layers between the user and the application. Starting from the outside, we have perimeter security at the hub level. This is where you implement centralized security inspection, whether through AWS Inspection VPCs, Azure's secured virtual hub with Azure Firewall, or GCP's router appliance spokes with third-party firewalls. This layer inspects traffic flowing between spokes and can block malicious traffic, enforce URL filtering, and provide threat intelligence. The next layer is network segmentation, which we discussed earlier. By dividing your network into segments and controlling traffic between them, you limit the blast radius if one segment is compromised. The diagram shows different segments for production, development, and management networks, with restricted traffic flows between them. Moving inward, we have VPCs or VNets level security through network access control lists and route tables. These provide stateless filtering of traffic at the subnet level. They're coarse-grained controls that apply to all resources in a subnet. At the instance or resource level, we have security groups or network security groups. These provide stateful, instance-level filtering. For example, you might allow your application servers to accept traffic only from your load balancers on specific ports. Security groups are typically easier to manage than network access control lists because they're stateful and you only define allowed traffic. Within the application, you have application-level security like authentication, authorization, input validation, and encryption. This is outside the scope of network architecture but is an essential layer of the security model. Encryption is the second major security principle. Encrypt data in transit and at rest. For data in transit, VPN connections provide encryption automatically. Traffic within a cloud provider's network can be encrypted using features like IPsec between VPCs, though this adds complexity. Many organizations accept that traffic within the cloud provider's network is sufficiently protected by the provider's physical security and logical isolation. For highly sensitive data, you can implement application-level encryption where data is encrypted before it enters the network. For data at rest, use the encryption features provided by storage services, databases, and compute instances. Identity and access management is the third principle. Secure access to your hub service configuration using strong authentication, ideally multi-factor authentication. Use role-based access control to ensure that only authorized personnel can modify network configurations. In AWS, use IAM policies to control who can modify transit gateway configurations. In GCP, use Cloud IAM with appropriate roles. In Azure, use Azure role-based access control to control access to virtual WAN resources. Enable audit logging for all configuration changes so you can track who made what change and when. Compliance requirements often dictate certain network architecture decisions. For example, Payment Card Industry Data Security Standard requires network segmentation between cardholder data environments and other networks. HEPA requires encryption of protected health information in transit. General Data Protection Regulation affects where you can store and process data, which influences your regional deployment strategy. Understand the compliance requirements that apply to your organization and design your network accordingly. Some compliance frameworks require specific security controls like intrusion IDS systems, which you can implement through network virtual NBAs in your hub architecture. Regular security assessments are crucial. Perform periodic reviews of your network configuration to identify misconfigurations, overly permissive rules, or unused resources. Use the security assessment tools provided by cloud providers, such as AWS Security Hub, GCP Security Command Center, or Azure Security Center. These tools can identify common security issues like publicly accessible resources, overly permissive security groups, or unused VPN connections. Consider engaging third-party security firms for penetration testing and security audits. Finally, have an incident response plan for security events. If you detect a security breach or anomalous traffic, you need a plan for isolating affected resources, conducting forensic analysis, and remediating the issue. Your hub and spoke architecture can facilitate this. For example, you can quickly isolate a compromised VPC by removing its attachment from the hub or by updating route tables to block its traffic. Practice your incident response procedures regularly through tabletop exercises or simulated incidents. Cost optimization strategies. Cost management is critical for sustainable cloud operations. Network costs can be substantial, especially in global architectures with significant data transfer. Let's examine strategies for optimizing costs while maintaining required functionality. Understanding the cost structure is the first step. Our diagram breaks down the cost components for each service. For GCP Network Connectivity Center, costs include spoke attachment fees, which are charged per hour per spoke, and data transfer charges, which apply to data flowing through the hub. Inter-region data transfer is more expensive than intra-region. There's no separate charge for the NCC hub itself. AWS Transit Gateway has a three-tier cost structure. First, there's an hourly charge for the transit gateway itself, approximately 5 cents per hour or about $36 per month. Second, there are per attachment charges of approximately 5 cents per hour per attachment. Third, there are data processing charges of 2 cents per gigabyte for data that traverses the transit gateway. These processing charges don't apply to traffic between VPCs in the same availability zone. Additionally, inter-region peering has its own charges. Azure Virtual WAN costs include the Virtual Hub Deployment Charge, which is approximately 30 cents per hour or about $220 per month per hub. Connection units are charged based on the aggregate throughput you need for VPN and other connections. Each connection unit represents a certain amount of capacity. Data processing charges apply to data flowing through the hub at around 2 cents per gigabyte. If you enable Azure Firewall in the hub, there are additional charges for the firewall deployment and for data processed by the firewall. The first optimization strategy is minimizing data transfer. Data transfer is often the largest network cost component. Strategies to reduce transfer include keeping data and processing in the same region when possible. If your data resides in US East and your processing happens in US West, you pay for cross-region transfer. Collocating them eliminates this cost. Use caching to reduce repeated transfers of the same data. Content delivery networks cache static content at edge locations. Read using origin fetches. Use efficient data formats and compression to reduce the volume of data transferred. A compressed JSON file might be 1/10 the size of an uncompressed XML file representing the same data. The second strategy is optimizing hub architecture. In AWS, consider whether you need transit gateways in every region or if a smaller number would suffice. Each transit gateway costs money, so consolidating where possible reduces costs. However, this must be balanced against the inter-region data transfer costs of routing traffic to a different region. In Azure, evaluate whether you need virtual hubs in every region. In GCP, since you have a single global hub, the optimization is in the number and type of spoke attachments. Right-sizing connectivity is the third strategy. Don't over-provision bandwidth. If you're using a 10 gigabits per second direct connect circuit but your peak usage is only 2 gigabits per second, you might be able to downgrade to a 5 gigabits per second circuit. Monitor your VPN connection utilization. If you have 4 VPN tunnels for redundancy but never exceed the capacity of 2 tunnels, consider reducing to 3 for a balance of cost and redundancy. However, always maintain sufficient capacity for redundancy and traffic spikes. Leverage cost-efficient connectivity options when appropriate. VPN connections are less expensive than dedicated connections, but offer lower performance. For non-critical workloads or lower volume connections, VPN might be sufficient. Some providers offer more economical tiers of dedicated connectivity. AWS offers hosted direct connect with smaller capacities that are less expensive than full direct connect. Azure offers express route local for traffic that stays within a metropolitan area, which is less expensive than standard express route. Review and eliminate unused resources regularly. Unused VPN connections, idle dedicated circuits, or orphaned VPC attachments all incur costs. Implement regular reviews of your network infrastructure to identify and remove resources that are no longer needed. Use tagging to track which resources belong to which projects or cost centers, making it easier to identify ownership and importance. Consider reserved capacity or committed use discounts where available. Some connectivity services offer discounts for longer-term commitments. If you know you'll need a dedicated connection for the next year or 3 years, a committed use discount might reduce costs by 20 to 40%. Evaluate whether such commitments make sense for your organization. Finally, use cost monitoring and alerting. Set up budgets and alerts in your cloud provider's cost management tools. Configure alerts to notify you if spending exceeds thresholds. Review cost reports regularly to understand where your money is going and identify optimization opportunities. Many organizations find that a small percentage of their resources account for the majority of costs, so focusing optimization efforts on the highest cost components yields the best return. Troubleshooting common issues. Even with careful planning, network issues can occur. Let's examine common problems and how to troubleshoot them across these 3 platforms. The first common issue is connectivity failures where one spoke cannot read another spoke. The troubleshooting approach is systematic. Start by verifying routing. Check the route tables in the hub service to ensure routes to both spokes exist. In AWS Transit Gateway, examine the route table associated with each attachment to confirm it has routes to the destination. In Azure Virtual WAN, check the effective routes for each connection. In GCP NCC, verify that Cloud Router is propagating routes correctly. Use CLI commands to inspect routes. For AWS, use the command AWS EC2 describe transit gateway route tables to view routes. For Azure, use a Z-Network vHub route table list. For GCP, use G-Cloud Compute Routers Get Status to see learned and advertised routes. Next, check firewall rules and security groups. Even if routing is correct, traffic might be blocked by security controls. In each spoke, verify that security groups or network security groups allow the traffic. Check network access control lists at the subnet level. If you have security appliances in the path, verify their firewall rules. A common mistake is forgetting to allow return traffic. If you allow outbound connections from spoke A to spoke B, you also need to allow the return traffic from spoke B to spoke A. Verify that spoke attachments are in a healthy state. A VPN connection might show as connected but be experiencing routing protocol issues. Check the status of BGP sessions. If BGP is down, routes won't be exchanged even if the tunnel is up. For direct connect or express route, verify the physical connection is active and the virtual interface or circuit is provisioned correctly. The second common issue is performance problems, where connectivity works, but latency is high or throughput is low. For latency issues, use tools like traceroute to identify where delays are occurring. From an instance in one spoke, traceroute to an instance in another spoke. The output shows each hop in the path and the latency to that hop. If latency spikes at the hub, there might be congestion or misconfiguration. If latency is high throughout the path, the issue might be with your internet connection for VPN or with your dedicated connection. For throughput issues, check whether you're hitting service limits. AWS Transit Gateway has a limit of 50 gigabits per second for VPN connections. Azure Virtual WAN scales to 20 gigabits per second per hub. If you're hitting these limits, consider scaling across multiple hubs or using direct VPC/VNet connectivity for high bandwidth workloads. Check VPN tunnel utilization. A single tunnel typically provides around 1.25 gigabits per second. If you need more throughput, use multiple tunnels with equal cost multipath routing. Verify that your instances are not the bottleneck. Network performance in cloud environments depends on instance size. Larger instances have higher network bandwidth. An AWS T2.micro instance has much lower network capacity than a C5.9x large instance. If network tests from instances show low throughput but tests from larger instances show better performance, instance sizing is your constraint. The third common issue is routing loops or asymmetric routing. A routing loop occurs when traffic circulates between routers without reaching the destination. This usually results from misconfigured route advertisements in BGP. Verify your BGP AS path to ensure routes aren't being re-advertised back to where they came from. Use BGP communities or AS path prepending to control route advertisement. Asymmetric routing occurs when traffic from A to B takes one path, but return traffic from B to A takes a different path. This is particularly problematic for stateful security appliances that need to read both directions of a flow. AWS Transit Gateway Appliance Mode addresses this for certain scenarios. Azure Virtual WAN can use routing policies to enforce symmetric routing. In GCP, router appliances need to be configured to handle asymmetric flows, or routing must be designed to ensure symmetry. Domain name system resolution issues are another common problem. Instances in one spoke might be unable to resolve domain name system names for resources in another spoke. Verify that your domain name system resolvers are accessible from all spokes. If you're using private domain name system zones, ensure they're associated with all VPCs or VNets that need access. For hybrid scenarios, implement domain name system forwarding between on-premises and cloud. AWS Route 53 Resolver, Azure Domain Name System Private Resolver, and GCP Cloud Domain Name System can forward queries between environments. Finally, authorization and authentication failures can look like network problems. An application might fail to connect to a database not because of network connectivity but because of incorrect credentials or security group rules denying the connection at the application layer. Always test at multiple layers. Verify network connectivity with simple tools like Ping or Telnet, then test the actual application protocol. Future trends and recommendations. As we conclude this presentation, let's look at emerging trends in cloud networking and provide final recommendations for choosing between these hub services. Several trends are shaping the future of cloud networking. The first is increased automation and infrastructure as a service. Manually configuring network infrastructure through web consoles doesn't scale for large environments. Organizations are increasingly using tools like Terraform, Pulumi, or native infrastructure as code solutions like AWS CloudFormation, Azure Resource Manager templates, or Google Cloud Deployment Manager. These tools let you define your entire network architecture as code, version control it, and deploy it consistently across environments. The hub services we've discussed all have comprehensive support for infrastructure as code. Adopting these practices improves consistency, enables rapid deployment, and reduces human error. The second trend is convergence of networking and security. Traditional separation between network teams and security teams is breaking down. Concepts like Secure Access Service Edge, or SASE, combine network connectivity with security functions like firewall, secure web gateway, and zero trust network access into unified cloud services. Azure Virtual WAN's Secured Virtual Hub is an example of this convergence, integrating routing and firewall in a single service. We're likely to see more integration of security into hub services across all providers. Multi-cloud and hybrid cloud are becoming the norm rather than the exception. Most enterprises use multiple cloud providers and maintain on-premises infrastructure. The hub services are evolving to make multi-cloud architectures easier. We're seeing improved interoperability, more standardized APIs, and better tools for managing multi-cloud networks. Service meshes and software-defined WAN solutions increasingly provide unified management across clouds and on-premises. Edge computing is another significant trend. As 5G networks roll out and Internet of Things devices proliferate, there's increasing need to process data closer to where it's generated. Cloud providers are extending their services to edge locations. AWS has wavelength zones in 5G networks. Azure has Azure Edge zones, and Google has Google Distributed Cloud Edge. These edge locations need to integrate into the hub and spoke architecture, creating more complex but more performant topologies. Application-aware networking represents a shift from traditional network routing based solely on IP addresses and ports to routing based on application identity, user identity, and context. Technologies like service mesh in Kubernetes environments provide application layer routing and security. While the hub services we've discussed operate at the network layer, they're increasingly integrating with application layer technologies. Now, let's provide recommendations for choosing between these services. Choose GCP Network Connectivity Center if you prioritize simplicity and global by default routing. If you're heavily invested in Google Cloud and want tight integration with Google's services, if you need excellent router appliance support for integrating third-party network functions, or if you want to leverage Google's global backbone for optimal inter-region performance. NCC is particularly strong for organizations that operate globally and want seamless worldwide connectivity without managing regional boundaries. Choose AWS Transit Gateway if you operate primarily in AWS and want deep integration with AWS services. If you need regional control for compliance or data residency. If you require multicast support for specific applications. If you have complex network segmentation requirements that benefit from multiple route tables. Or if you're already using AWS Direct Connect and other AWS networking services. Transit Gateway is particularly strong for large AWS-centric deployments with sophisticated routing requirements. Choose Azure Virtual WAN if you have significant branch office connectivity requirements and want to leverage Azure's SD-WAN partnerships. If you need integrated security with Azure Firewall in the hub. If you're using Microsoft services like Azure Active Directory, Microsoft Office 365, or Dynamics and want tight integration. If you need native point-to-site VPN for remote users, or if you want automatic scaling of VPN capacity without manual sizing. Virtual WAN is particularly strong for organizations with distributed branch offices and those invested in the Microsoft ecosystem. For multi-cloud scenarios, consider using multiple hub services together, connected via VPN or through a third-party SD-WAN provider. Each cloud's hub service excels within that cloud, and connecting them provides the best of each platform. Thank you for your attendance. Please consider subscribing to the channel and liking this video.